Right, hello everyone. My name is Guy Davidson. We're at Meeting C++. This is the 15th of November 2018. And I'm here to talk about standardizing a linear algebra library. This is the first time I've given this talk. I suspect it won't be the last, because the process of standardization is a long journey, a very long journey, an odyssey, an epic, full of monsters and setbacks and all sorts. I'm used to this. Dragons, there may very well be dragons. Pardon? Nasal dragons? I'd like to keep those to a minimum, optimally. Here's what to expect, representing linear equations. Right, the numbers in square brackets are the slide numbers. You'll notice the slides go up to 238. Do not be alarmed. I don't like mucking about with all this introducing special effects into slides, so the special effects are simply fresh slides. I just think it's safer that way. So we'll take a quick look at what is meant by linear algebra, what it's used for. We'll be looking at typical libraries to solve linear equations. Then we'll look at dynamic and sparse matrices and MD span, things like that. Then we'll look at promotion. Then the importance of customizability of operation engines. You'll know what an operation engine is shortly. Things like Strasson's algorithm or Coppersmith-Winograd and Struthers-Williams, although I'm sure you wouldn't actually want to implement those. And then we'll look at the API from the ground up. First of all, I want to talk about our goals. So I'm co-authoring this presentation with Bob Stiegel, who is an excellent man to be having on board. So what we want to do is to provide linear algebra vocabulary types that mimic those found in textbooks, applicable to a wide variety of problem domains like graphics, games, which is my domain, image and signal processing, large simulations, that sort of thing. We want to use templates to parameterize the orthogonal aspects of representation. And of course we want default templates for most people. Default template parameters and aliases that serve the needs of the 90%, rather than the 10% of power users who are really keen for squeezing every last cycle out of their processors. And it needs to be customizable for power users so they can gain maximum performance on their specialty platforms. That's particularly what's important here. We need element access for matrix arithmetic and fundamental operations. We need facilities for solving the common least squares and eigenvalue problems. And we need to support mixed precision and mixed representation expressions such that precision is never lost. A bit of a tall order. I think we can do this. Let's talk about representing linear equations. Now, linear algebra is the branch of mathematics concerning linear equations and linear functions and their representation through matrices and vector spaces. Now, for our purposes, we're going to concentrate on linear equations and matrices rather than anything else, because we're always going to be working in a finite dimensional space. Things get complicated with non-finite dimensional spaces on computers, obviously. So, just to remind you, this is what a linear equation looks like. So, AN, or A1 through AN, represents a coefficient, XN represents an unknown. Linear algebra is actually central to most of mathematics. And I'm going to look at three particular applications. The first is solving sets of simultaneous equations. Then we'll look at modern presentations of geometry for defining lines, planes, transformations, all that kind of monkeying around. And then we'll consider linear regression. And I'm going to ask straight away, how's your maths? Everyone got their maths heads on at 5:15 at the end of day one of Meeting C++. Everyone, yeah, really good, all right. You're confident in your linear algebra. So I'm going to go through the fundamentals first, so that we're all working on the same page. But stop me if I'm not being clear enough. I haven't actually taught this for quite some time. So a vector is a tuple of scalars. I pronounce it tuple. I do not pronounce it tuple to rhyme with supple. I pronounce it tuple to rhyme with tuple, like quadruple. I'm very particular about the pronunciation of tuple. Now you can perform addition, and you can of course perform the inverse operation, subtraction, if they have the same dimension. So they both have to be n-dimensional tuples. You can perform scalar multiplication like this, and you can perform vector multiplication like this. A row vector times a column vector. This is significant. And this is called the inner product, or dot product, particularly. A matrix is a tuple of vectors. Again, you can perform addition and you can perform the inverse operation if they have the same dimension. Scalar multiplication is also available. Multiplication of matrices is a little more complicated. I hope you will recall that it's a bit of a pain, since the source column count must be the same as the target row count. Significantly, multiplication is not, in general, commutative. Now, there's a special kind of matrix called a square matrix. There's a special kind of square matrix called an identity matrix. There's a bit of layout nonsense going on there. It's really hard to lay out mathematical stuff on slides, and I just gave up. I'm sorry. Life's too short, really. If I were publishing a book, this would all be different. I'm not. It's not. Right. A square matrix can have a determinant. Geometrically, it can be viewed as the scaling factor of the linear transformation described by the matrix. So determinants crop up a lot. And then we have a matrix can have an inverse such that an inverse is, if the matrix is multiplied by its inverse, or the inverse is multiplied by the matrix, then you get the identity matrix. Not all matrices have inverses. Now, this is rather reminiscent of the built-in types, although increment and decrement and ordering are obviously unavailable. Well, you could try writing an ordering operator. I might have to ignore you if you did so. Are we all clear so far? That's, that's a basic primer, 101. So let's look at solving simultaneous equations. It's actually a simple matter. So let's look at this system of equations. Now, you can see the important differentiation between row vector and column vector. So ax plus by equals e becomes ab on the top row of the matrix times xy in the column vector equals e as the first element of the corresponding column vector. So we can call that first matrix A and rewrite it like that. And then what we can do is we can rearrange this by multiplying through by A inverse. That's if it has an inverse, of course. So let's try an example. 2x plus 3y equals 8. X minus 2y equals negative 3, which makes A 2, 3, 1, negative 2. Now, the inverse of a square matrix is the reciprocal of the determinant times the classical adjoint. We all remember this, don't we? Yes, just say yes, guy, and we can get on, all right? So these are trivial to calculate for 2 by 2 matrices. The determinant is 2 times negative 2 minus 1 times 3, which equals negative 7. While the classical adjoint is this. You swap the elements of the leading diagonal, and you swap the signs of the other diagonal. Calculation of these is rather less trivial for higher dimensional matrices. This is why I'm doing 2 by 2 examples. We can worry about all this later. I know I'm cutting corners. I have an hour. This makes A inverse negative 7 to the negative, well, reciprocal of negative 7 times the classical adjoint. So, given that value for A inverse, we've got xy equals reciprocal of negative 7 times that column vector. Let's do some sums. Believe me, that's right, okay? You can check the slides in the recording afterwards. So x equals 1, y equals 2, and we can check that. 2x, 2, plus 3y, 6, equals 8. Yeah, thank you. I'm not Stephen Hawking, but I think I've got a chance at the Lacasian chair. I think, Right, let's go back to the general form of a linear equation. We can migrate this to the 2D plane. Now, with a little substitution, I'll make this clearer. So, more familiarly, we can turn this into ax plus by equals c, where I'm just substituting x1 and x2 for x and y. They're just letters. They're just unknowns. So this becomes by equals negative ax plus c, which is effectively y equals mx plus c, the very familiar equation for a straight line. I hope that's familiar to you all. So we can see that any straight line can be represented with a linear equation. So generalizing to 3 dimensions, you can see how this would work for planes. Now, representing a coordinate pair as a vector, we can translate, scale, shear, reflect, and rotate this vector. So translation takes place by adding the translation to the coordinate pair. like that. Scaling works like this, either by a scalar multiplication, or we can actually achieve the same effect with an identity matrix times the scalar. Shearing means scaling x and y by different amounts, which we achieve like that, and reflecting means multiplying a particular ordinate by -1. Rotating is slightly more complex. It just is. If we want to rotate a point around the origin by a radians, we'd use this matrix, which, as you can see, evaluates in that way. We can stack multiple operations by multiplying matrices. If we want to reflect and shear, we can do so like that. This is useful for carrying out the same operation on a set of points. If you have a picture on, in 2D space and you want to reflect and shear the whole picture, and the picture is made up of a series of points, if it's a vector diagram or something like that, you can just apply the one operation to all the points rather than applying two operations to all the points. Now, linear regression is a linear approach to modeling the relationship between a dependent variable, y, or a scalar response, and an independent variable, x, also known as an explanatory variable. Linear regression can be used to fit a predictive model to an observed data set of values of the response and independent variables. So particularly, given a data set of n statistical units, a linear regression model assumes that the relationship between the dependent variable y and this vector of regressors, x, is linear. And this relationship is modeled through a disturbance term, or an error variable, epsilon, an unobserved random variable that adds noise to the linear relationship between the dependent variable and regressors. So the model takes that form, where the superscript capital T represents the transpose. You can see this on the x. So that xi transpose times beta is the inner product between the vectors of xi and beta. So often these equations get stacked together and written in matrix notation, where you make everything bold like that. So y is a vector of observed values. Now x can be seen as a matrix of row vectors, known as the regressors, and sometimes it's called the design matrix. And usually a constant is included as one of the regressors, as we have there in the first column. The corresponding element of beta is called the intercept, and many statistical inference procedures for linear models require an intercept to be present, so you often include one, even if theoretical considerations suggest its value should be 0. It just makes the sums more calculable. Beta is a parameter vector, where beta 0 is the intercept term. Now, its elements are known as effects, and statistical inference and estimation in linear regression focuses on this matrix beta. And epsilon is a vector of values. This is all the noise. It's called the error term. It captures all the other factors besides beta which affect the dependent variable y, other than the regressors x. So the classic example is throwing a ball in the air. What you do is you measure its height at various intervals, and a bit of integration tells you that the relationship can be modeled like that. That's just Newtonian physics there, really. So beta 1 determines the initial value, velocity of the ball. Beta 2 is proportional to gravity. And epsilon is due to measurement errors, maybe a bit of drag, that kind of thing. And linear regression can be used to estimate the values of beta 1 and beta 2 from the measured data. It's jolly clever, really. This model is non-linear in the time variable. You'll see that the gravity term is actually is time squared, but it is linear in the parameters for beta 1 and beta 2, which is why the regression works. So if we take regressors, the model takes on the standard form. This isn't a statistics lecture, but you can see there's going to be a lot of matrix multiplication going on here, a lot, particularly for gathering lots and lots and lots of data. So there's a lot of application for linear algebra. Linear regression is used extensively in AI classification. Right, enough theory. Who's actually here written a linear algebra library? Who's written 2 linear algebra libraries? Who's written 3 linear algebra libraries? Who's written 4 linear algebra libraries? Okay, I dug out my notes from nearly 30 years ago when I wrote my first one, and I discovered that my first linear algebra library used fixed-point arithmetic on a 286 PC without a maths coprocessor. And I wanted to use SI units and 16-bit fixed point arithmetic, so I reserved 4 bits for the fractional part, giving me 6¼ centimetre resolution. My next one exploited the floating point coprocessor that shipped as standard with the 486 processor. And then I made use of the SSE2 instruction set on a Pentium 4. And now I've got a revised version of that running at the moment with AVX instructions. I think it was on the Sandy Bridge processor since about 2011. I'm a game developer, so my use of linear algebra was strictly limited to matrices with between 2 and 4 rows and columns with a non-integer scalar type. So I have several optimizations available to me. I know how big all my matrices are going to be. The scalar type is always the 32-bit floating point type. And I know about my target processor. You know, I tell people who buy my games, you need this processor or better inside your computer. So I can use intrinsics and I can use SIMD instructions. And I can make use of cache behavior. But my library is optimized for this particular usage. Okay? Everything is fixed size, everything is dense, and there are many ways to optimize for other situations, such as sparse matrices of variable size. But that doesn't matter to me in my domain. But it's like string classes. Who has written a string class? Who has written 2 string classes? Who has written 3 string? Oh, come on, really? None of you have written 2 string classes. I find that extremely hard to believe. Oh, you're all modern C++ programmers, aren't you? Why rewrite a string class? I can give you a few reasons, but I won't in this talk. Right. But everyone can write the best string class for their needs. You know, that's the thing. You know, is it worth it? Is it worth writing a better string class? Yeah, you know, decreasingly so as time goes on. There are quite a few matrix libraries out there already. I just did a simple Wikipedia query, and I got so many that I didn't know about. And I thought, I know all these, and there are so many. Let's take a look at 3. So the one we all know about is BLAS. Do you know about BLAS? Who doesn't know about BLAS? It's all right. All right, who does know about BLAS? Right, okay, good. Basic linear algebra subprogram. So this was first released in 1979, when I started programming, as a Fortran library. And it prescribes a set of low-level routines for performing common linear algebra operations. There are C bindings as well, so that's handy for us. And there are many implementations optimized for speed on a particular machine. But again, many implementations. There's a C++ API, which is called BLAS++, because imagination is not at the top of our skill set. And this implements much of the functionality for your linear algebra needs. Here's an example function, BLAS_AXP. Particularly, it supports single and double floating point precision and single and double precision complex numbers. So 4 types there, so there's 4 of everything. There's also, of course, boost.ublas. But the last significant change to that library was in 2009, which means we don't have constexp, we don't have no-except. And not having no-except, bit of a killer for me. So there are 3 levels to the BLAS API. I'm not going to... You can read those, or you know them. But level 1 contains the vector operations. Level 2 contains the matrix vector operations. And level 3 contains the matrix-matrix operations. And this gives us a good starting point for the kind of API that we might want. You can see a fair amount of repetition varying on matrix type. So we've got Hermitian and symmetric and triangular matrices. And our operands. We've got matrix vector operands and matrix-matrix operands. And the set of operations is different for vectors from matrices. Eigen. So this is a significant advance over BLAS. First, has anyone used Eigen? Okay, it's huge, isn't it? It's enormous. It is about that big. Maybe that big, actually. I don't know. That. Is it about that big? That? I don't know. It's thorough, it's comprehensive, it's great, but it's huge. So it consists of a selection of class templates for matrices, vectors, and operations. And it accommodates runtime as well as compile time sizes. And it has a mechanism for dealing with non-owned data through the map class. So if it doesn't own the data, it's just inspecting data that's being presented to it. All right, how many member functions does string have that aren't the special functions?
170.
What?
170.
No, less than that. It's 45. Yep. Stood string has what? I counted them. Maybe I was counting them incorrectly.
this in 2001. It was 150.
Really?
They added.
Okay, I'm going to look again. I opened up cppreference.com.
All the overloads because then
Oh, yeah, I probably did. Okay, so yes, it looks like I didn't count the overloads properly. All right, scratch this from the video. I don't want to look stupid. Okay, thanks. You're not going to do that, are you? I can tell. Right, okay. Actually, that's the thing I dislike about Eigen, is it has an API that's defined entirely through member functions, and we've got bad experience of rich member function API for classes like string. And we don't want to repeat that with linear algebra. You know, once is enough. Not even once is enough, in fact. And there are so many things that might be required. You know, BLAS++ offers 32 functions. Oh, you know. So the Eigen tutorial offers this sample program. It's quite easy. Well, I think it's quite easy to understand. I quite like it. I can see what's going on. It could be because I'm a mathematician, but, you know, I quite like the comma initialization through the chevron operator of the vector. All right, anyone use DLib? Now we're thinning out, aren't we? This is a big library of useful things, basically. This is just oh, look, here's a big basket of nice stuff for you to use. It takes an interesting approach to matrices by deploying expression templates. Did I just get an ooh there? Right. In an attempt to achieve efficiencies, I'm going to explain quickly expression templates. Strap in. Okay. Now, the idiom was described by David van der Voort and Todd Veldhuizen at about the same time. Now, they're a template metaprogramming technique that builds structures representing a computation at compile time. Okay, where expressions are evaluated only as you need them, only when they need executing. And it produces efficient code for the entire computation. And it allows you to bypass normal orders of evaluation, and you can do things like, you get optimizations like loop fusion, which is really handy if you've got big matrices. So look at this class. Simple row vector class. You've got a constructor, you've got some access operators, and you've got the data itself. A vector of floats for the elements. And we have an operator plus, where you simply iterate through all the... Yes, it's a raw loop. Get over it. You iterate through all the elements of each, and you add them all together. So what happens if you want to sum 3 row vectors? So a temporary will be created for the result of the first sum, and this will require 2 loops. Now, delayed evaluation solves this problem and can be implemented in C++ by letting operator plus return an object of a custom type, say row vector sum. And that represents the unevaluated sum of 2 vectors, or a vector with a row vector sum, adding a vector and a row vector sum, for example. So larger expressions then effectively build expression trees that are evaluated only when assigned to an actual row vector variable. But this requires traversing such trees to do the evaluation, which obviously is in itself costly. And expression templates implement delayed evaluation using expression trees that only exist at compile time. Each assignment to a row vector, such as row vector x equals a plus b plus c, generates a new row vector constructor, if needed, by template instantiation. And this constructor operates on the 3 row vectors. So it allocates the necessary memory, and then it performs the computation. So only one memory allocation is performed on the stack or on the heap, or wherever it is. Right, here's an example. So a base class vector expression represents any vector valued expression. So it's templated on the actual expression type E to be implemented. And this is an example of the curiously recurring template pattern, which I'm sure you've probably all heard of. The row vector class still stores the coordinates of a fully evaluated vector expression and becomes a subclass of vector expression. So let's add a couple of constructors to the class. No magic there, I'm sure you can see. So a row vector can be constructed from any vector expression, forcing its evaluation. So the sum of 2 vectors is represented by a new type, vector sum. And that's templated on the types of the left and right-hand side of the sum so that it can be applied to arbitrary pairs of vector expressions. An overloaded operator plus serves as syntactic sugar for the vector sum constructor, like that. And with the above definitions, the expression a plus b plus c is actually of this type, which is quite the mouthful, I appreciate. So row vector d equals a plus b plus c invokes the templated row vector constructor with this type as its e-template argument. So inside this constructor, the loop body is effectively expanded, following the recursive definitions of operator plus and operator square on this type to that, which is groovy. No temporary vectors needed and only one pass through each memory block. Okay? This is a significant efficiency which we need to be able to enable implementers. Expression templates do get quite complicated quite quickly, and they can balloon really hugely without too much effort. But the efficiencies they offer are not to be sniffed at, and if you think this is cunning, is Hannah in here? Anyway, you should go and see Hannah's compile time regular expression talk. That's far more interesting than this one, really. So the point I'm making is there are many different libraries out there with different goals and different ways to achieve optimal performance. This is a bit of a problem, because the job of the committee is to standardize existing practice, not design new stuff. So this puts us in something of a pickle. How do we accommodate the best of everything? Well, we don't. We expose customization points. So let's look at the first one. Everything you need to know about storage. So storing your matrices is quite the topic. If you're using a fixed size matrix, then you can most likely simply keep it on the stack. But if you're using a sparse matrix, or you don't know the size of the matrix until runtime, you'll need to be able to allocate memory on the heap, or wherever you're keeping your free store. Alternatively, you may not own the values that make up the matrix. What if you have a stream of scalars of known stride coming at you, and you simply want to span? And let's also not forget cache requirements. You know, how big are your cache lines? How do you want to store an array of matrices? Do you have access to SIMD instructions? Which set? How big are the registers? How many do you have? Does your tool set expose intrinsics? Much of these are implementation details. And the purpose of standardization is to define an API, not necessarily an implementation. So the obvious solution is to parameterize your storage and standardize how you access the elements. So let's introduce our first class, fixed size matrix. It's a naive class. Okay, that was easy. I can go home now, really. That's it. I think we're all done, aren't we? Yeah. All right, what sort of things might I want to do? Well, I might want to know the number of columns, but we can establish that from the template parameters, as we can the row count as well. Maybe I want direct access to the data, rather than having it private. Maybe I just want to be able to make it public, or maybe I'm quite happy with the function operators there. One thing I'd really like, is a two-parameter square operator accessor, as you see at the bottom there. I can't write matrix ij, at least not yet. There are moves afoot from Isabella Muerte to enable that. Once this class, or whatever flavor of it we're going to have, enters the standard, it would be wonderful if somebody would actually propose that. But I'm going to be busy. I've got a lot on at the moment. The scalar type name is an ideal candidate for a concept as well, I think. But what if you don't own the data? What if it already exists somewhere in a consumable form, and you don't want to expend cycles, memory, and energy copying it somewhere else to deal with it? What if I told you there's already a proposal to add a multidimensional data view to the standard? Well, of course, this is in fact the case. P0009, so it's quite an old proposal, several years in the making, but it is upon us, and it's working its way through the library working group, and may yet make C++20, although it's looking tight. And this would give us our next class, matrix view. All right, what's going on here? We have to expose the scalar type somehow, so we do that through a using declaration. There's no initializer list construction because we don't own any data. And then we have to retrieve the rows and the columns by querying the MD span. And this looks not too different from the fixed size matrix, really. If you're familiar with the paper, the MD span paper, you'll know that there are quite a lot of MD span constructors, a big lot, a very large lot of constructors, which might require them being included in the class as well, so that they can be forwarded to the mspan data member that we have down there. I do recommend reading the paper, get a grasp of what's going on. It's very interesting, very comprehensive, good bedtime reading. These matrix classes rely on you knowing at compile time how big things are going to be. But that's ideal for my traditional domain. Data harvesting, though, is rather less so. Perhaps data is arriving and you want to periodically grow a matrix with additional rows, which means we have to drop the row and column parameters and replace them with an allocator. So how about this, dynamic size matrix? Again, nothing too surprising there, I hope. We've got the columns and rows functions. One would hope they're no except, and they're bound to be const. We've got the accessors, we've got an initializer list, as well as a default constructor. But now we're looking at a container. Okay, now we're looking at a container. We have to add column and row member functions to query the size of the matrix, and also reserve and resize functions because containers. That's what you do with containers. And we should add the row and column query functions to the fixed size matrix and to the to the other two matrix classes, so that we don't need to know the type of the matrix to get that data. Reserving and resizing are not required in that class because those functions are only going to be called when more data is to be added at runtime, not something that's the case with fixed size matrices, for example. So these are the three that will feature in the first draft of the proposal. Okay, but of course there's nothing to stop you specifying your own storage class for more exotic purposes, which we might get to if we have time. Right. Anyone here use C++ for performing arithmetic? None of you? Yes! Okay, people do arithmetic with C++. Great. Okay, quiz time. Right, standard interview questions, so do take note. I want you to look at this piece of code. I want to know the type and value of A, please. Ooh. Okay. Yes, it's not a trick question. How about this one? Is this a trick question? Oh, you're a reluctant and reticent audience, aren't you? It's a long. Value 11. 11L, obviously, because it's a long. This one? What do we think of this? Oh, good. You're all right. Yes, you don't like the look of this, do you? 0. Yes, an unsigned long. This trips up most of my candidates. Why isn't it signed? Why is it 0? Okay, -3 UL means the bit pattern of -3 interpreted as an unsigned long, which is an enormous positive value. Does that make sense? Good. On we go. I could do this all day. Right, it's a long, still 0. Same problem. Let's change tack a little. Yes, 11.666,666,666,666,666. That was the right number of sixes. That decimal point actually annoys me. I don't think this should be legal, but Kernighan and Ritchie disagree, so, you know. Next. You're all murmuring and disagreeing with each other, aren't you? I love the sound of this. It's exactly the same. 7 point, a double times a float divided by 3. Easy. All right, now what? Yes. And now it's starting to see rounding errors creep. Well, I say rounding errors, but you know. I love this one. You all hate yourselves, don't you? I love this one even more. All right, who says 0? Who says something other than 0? Who wants to go home and get out of this stupid lecture? Oh, the man behind the camera. Thank you very much. All right, I'll put you out of your misery. There it is. Because now we've got a very, very, very large number dividing a small floating point number, but a small floating point number with really very large quantity of precision. I could do this all day long. But we're talking about implicit conversion here, so who knows their promotion and conversion rules? Yeah. Oh, excellent. Would you like to come up to the front and tell us? No, right, okay. Right, small integral types can be promoted to large integral types. Okay, that's promotion. Arithmetic operators do not accept values smaller than int. Okay, so that's fortunate. Float can be converted to double without changing value. Conversions may change the values with potential loss of precision. With integral conversions, sign and width are important. Floating point conversions are a little more forgiving, although converting doubles outside the range of floats is undefined behavior, demon number 1. Floating point to integral conversions merely discard the fractional part. If it can't fit, it's undefined behavior. Integral to floating point conversions return the nearest value. Go to CPP reference com, search for integral promotion. It's a long, long page. But arithmetic is well defined. We know what arithmetic is. The C++ built-in arithmetic type freely promote from float to double or from int to long and freely convert from integral to floating point. And I'll reinforce that as I hear it incorrectly stated often. Promotion, float to double. Widening representation. Conversion, integral to floating point. Changing representation. Okay? So imagine not having that flexibility available to you. Okay? It would make life pretty hard because you would need to explicitly promote everything to the widest type or up to long double and then narrow everything back down again. Imagine the bookkeeping, the ugly casting everywhere. You know, this just happens. This is the swan serenely floating across the lake with its legs paddling away, and the legs paddling away is all the promoting and all the converting and all the business. But having said that, this actually used to cause me terrible trouble. Who knows what ftol is? Float along, yes. This is the implicitly called function when you write something like this. Yes. It's quite an expensive function. It has to be called at runtime, obviously, to convert the floating point representation of b times 3.5 to an integral type representation. And quite often, in the code that I was looking at and reviewing, the int type was just arbitrarily chosen, and a float would have been entirely appropriate. And I was delighted when auto appeared and became quite the convert, the cause of almost always auto, because it meant that all my ftols would disappear. If you have a matrix of int, and you add a matrix of double, you should get a matrix of double. Okay? How can we achieve this? Well, what we need is a new type called element promotion underscore t, which returns the resultant type of multiplying two types together. So we'll be proposing this in the paper. Now, this might seem a little trivial, but complex numbers, for reasons described shortly, complicate matters. But here's the walkthrough. We start with a trait to detect if the type is complex. The general case is false. We specialize that, which is true, as long as the type is actually arithmetic, of course. Otherwise, weird things are happening if it's not arithmetic, and we're not ready to go that far yet. We simplify with the Boole expression is complex V. And now we need a trait to detect if the type is a suitable matrix element. Is it arithmetic or is it complex? And again, we simplify with is matrix element V by taking the value of that. So now we can move on to promotion. So we have a type to resolve the element promotion type. Using Deckel type there. Doing all that work for us. And now we can simplify with element promotion helper T. Return type. And from that, we can create an element promotion struct. Type equals element promotion helper T. And specialize that for complex numbers on the right. This is where it gets frustrating. On the left. And for both, yes, well, may you laugh. I'm not laughing. But we can simplify that with element promotion underscore T, which is what we wanted. A type trait for establishing the element promotion type. But why all the shenanigans with complex numbers? Anyone here use std complex? Yeah, not many. There's not much love for std complex. So quiz time again. Well, who knows? No one, none of you. I'm not even going to bother. Right, there we are. 17-0, obviously. Yeah, run it through. I ran that through 3 compilers. That one. 17-0 again. That one. 11 2/3. Here we are. Hello, old friend. And this one. Malformed. How about this one? Also malformed. Now, does this obey the principle of least astonishment? No. No, it doesn't, does it? Should the compiler be able to evaluate this? Yes. Yes, it should. I think this is a defect in stud complex. What should happen, and in case you didn't get it, it's because you're multiplying a complex float by a complex over double, or a complex float by a complex over int. You're multiplying 2 things for which operators aren't defined. You'd have to actually write your own operator overload yourself. One isn't provided. So what should happen is that the promotion of the scalar type should be reflected in the return type template parameter. And if anyone wants to write a proposal to correct this, I'd be very happy to help you out here. As I said, I'm a bit busy right now. But while you're at it, make it no except constructible for no except constructible scalar types as well, please. That'd be handy. But back to linear algebra, we need to specialize our element promotion for stud complex because that type admits no conversional promotion. And you might be asking yourself, is it really worth all this furniture? When am I going to need a matrix of complex numbers? Anyone want to offer an answer? Yep, quaternions. Yes, quaternions, I use those. There's another problem. What if we want to operate on 2 matrices with different storage types? Okay, that's a thing. It seems we need to describe a system of conversion for storage types as well as scalar types. But I think this is quite simple to grasp. I'm going to look at these examples. What should the type of the result be? I think it should be fixed size. What about this one? I think that should also be fixed size. But if we multiply a fixed size matrix by a dynamic size matrix, it's going to be dynamic size. We don't know how big it is. If we multiply a view by a fixed size, it's going to be fixed size. If we multiply a view by a view, that's also going to be fixed size because we don't own the data and we're creating something which has a different result, which will be data that we do own. Matrix view times dynamic size again, dynamic size. Dynamic size times fixed size, dynamic size times dynamic size. If you've got dynamic size in there, it spreads like a virus. If we decide there are 2 qualities to consider, owning versus non-owning, and fixed size versus dynamic size, then I think owning trumps non-owning, and dynamic size trumps fixed size. So we've covered storage and promotion. Let's look at operations. We want to add, subtract, multiply, and divide by scalars, and multiply by other matrices. How we do that depends very much on what you're actually doing. So for example, this is the naive way of multiplying a matrix. You iterate through the rows of the source matrix, and you multiply by the columns of the operand matrix. However, you may know that your matrices contain lots of empty rows or columns, and you might choose to flag those to speed things up. But that is a different algorithm. How do we enable the user to choose their own algorithms? Well, I'm sure you've guessed, it's another customization point. So let's look at what we have to customize. So row and column vectors have special operations that come in useful. These are the inner products, modulus and unit vector. Let's look at a naive implementation of each of these. The inner product symbol already has a definition in the standard library, which I didn't know. The things you find out when you write a paper. So it would be a case of simply forwarding to that function. Modulus is again quite trivial. We provide 2 functions, modulus squared and modulus. So we have modulus squared, which I hope that's self-explanatory, and modulus, which takes the square root. And finally, we have unit vector. Transform all of the elements by dividing them by the modulus. All matrices and vectors can be transposed. So transpose would look like this. It should also be possible to simply provide a transpose view on a matrix, so that you don't end up, going through all these operations, but actually all our accessor operations could treat it as a transpose. You have a transpose view on.
Do you also want to transpose a row vector and get a column vector?
Could you repeat the question, please?
Do you want to transpose a column vector and get a row vector?
Maybe. Do you want to transpose a column vector and get a row vector? Sorry, asked to repeat the question. Thank you. You might want to. I'm not going to rule it out. It's probably harder to prevent that than it is to allow it. I can't think of any immediate applications, but, I can't see the future. It'd be great if I could. It would make writing this paper a lot easier. It should also be possible to simply provide a transpose view. That's the point I'm making. Just move things around. So next we have submatrix. This pulls a matrix out of another matrix by masking out a column and a row. It would look like this. And obviously it's 1, 1 because it's maths, not C++. I'm talking about the theoretical part here. Again, this is a naive implementation. Just iterate through everything, masking out the stuff that's not in the row and column. And then we have inverse and invertible. Finding the inverse is not computationally trivial. For non-square matrices, you need to use the more Penrose algorithm. I'm not going to throw a slide of code at you for this, but there are many ways to calculate it. Square matrices have a few additional functions. So the identity matrix is the matrix which leaves matrices unchanged under multiplication. So generating one looks like this. Again, we can look at the slides on the recording. The determinant is a little less trivial. This is a recursive algorithm with the use of if const extra there, Alexei. All right, no, okay. Use of if const extra there for base cases. So we're finding all the determinants. We're finding the determinants of all the submatrices here. You can see, the magic is taking place in the determinant submatrix. And we're using if const extra for the base cases. The classical adjoint is used in calculating the inverse of square matrices. You take the reciprocal of the determinant, and then you multiply it by the classical adjoint to get the inverse. This is rather easier than the more Penrose. I don't necessarily think actually exposing this in the API is a good thing on reflection. There are very few uses for it. This is our set of functions. So they need to perform conversions. So they're function templates returning auto. Let's put them in a struct and template them over a storage type. Now, what's significant about this set of functions is that some of them are deeply non-trivial, particularly inverses. And there is an extant body of work which describes different approaches to take depending on the nature of the matrices. Taking a look at multiplication, at worst, to multiply two n-square matrices requires n cubed multiplications of scalars and n squared minus n additions. That's a lot of work. So this means the complexity is O(n) cubed, although there are cache considerations to bear in mind that aren't a part of the complexity calculation, which, I think big O notation might be running out of steam with the effect that cache will have. But the ubiquity of matrix multiplication, as I demonstrated before, this has inspired a lot of research into superior algorithms. Anyone familiar with Strasson's algorithm? It's a bit specialist, I agree. So that's got complexity of O(n) to the power 2.807, precisely, which is less than O(n) cubed. So, that's a reason to use it. And there's been a race to minimize that value over the past 50 years. Strasson's algorithm first turned up in 67 when I was born. As of 2014, that complexity number has reached that, 2.372869. And there's been research into Gaussian elimination, matrix inversion, determinant calculation, all for the same reason, leading to all manner of handy algorithms for particular circumstances. We cannot therefore require clients of the class to use a particular algorithm. So that means we have a second customization point, the set of algorithms that you want to use for operations on this matrix or vector. Okay, 2 customization points. You may decide on an expression templates implementation, or you may decide that the compilation burden is too great and decide on something more naive while prototyping, just so you can get rapid compilation going through. So let's put all this together. We have a storage class. We have an operations class. But neither of these are what we want for our users. We want a matrix class, we want a row vector class, and we want a column vector class. So let's look at these classes. First of all, we've got the scalar T and matrix T types at the top there. They are inferred from the template parameter. And you can see a selection of constructors. This isn't exhaustive. I'm sure there will be more. This is just partial exposition. You can see construction from an initializer list and construction from a pair of dimensions. Then we have const and non-const access to the matrix data and the elements via row and column. Equality operators, scalar multiplication and division, addition and subtraction, and finally the data itself. And then there are non-member functions. Okay, so that's the end of the member functions. Op equals, that's pretty much it, accesses. So we've got the scalar binary operators for multiplication and division. Then we have some matrix functions, transpose, submatrix is invertible, and then a function for testing whether or not it's the identity. And these are the matrix binary operators for addition, subtraction, and multiplication. We've got some square matrix functions. Yeah, I'm going to ditch classical adjoint, I think. Generate an identity matrix, calculate the determinant in the classical adjoint, and calculate the inverse. And the vector functions. This is not exhaustive. Vector multiplication needs a couple more functions, and there's scope for adding still more non-member functions. But there is a single template operator, rep, for representation. And you might be able to work out what this looks like. Brace yourselves. That is quite a mouthful. It's a very verbose spelling. So more on this in a moment. Now, the key takeaway from this presentation is this. Okay? Storage and operation are, in the general case, orthogonal concerns. They are orthogonal concerns. You might be able to devise operations which rely on storage. Okay? You might be able to devise operations that take advantage of the way that the data is stored. But that tighter coupling will always be solution domain specific. So that should not be made in the standard. Serious. Okay? So what do we deliver to the standard? Out of the box, I think we need to deliver something immediately useful and sufficiently performant. I think we should deliver the matrix, the row vector, the column vector class, one operations class, and the fixed size and dynamic size storage classes. And if MD-span makes it through LWG before this proposal, probably will, then the matrix view storage class should also be added. Now, how do we teach this? What are we going to tell our students about using these classes? Now, assuming your students have a knowledge of linear algebra, and assuming we get classes to behave without astonishment, with conversion and promotion similar to the built-in types, there shouldn't be too much to teach. There really shouldn't. It should simply work as assumed by the user. Principle of least astonishment. It's great. A row vector multiplied by a column vector should create a scalar. A column vector multiplied by a row vector should create a matrix. Mismatched vector addition should fail to compile or should report an error under contracts. Everyone up to date with contracts? Read about contracts. They're amazing. They're great. It's a C++20 feature. You'll love it. It reduces the quantity of exception handling required in the standard library as well, and that's also a good thing. There is, however, one rather glaring point that will require careful study, and that's the rep type, as I demonstrated earlier. So let's go back to those declarations. This is fearsome for the newcomer to the language. It really is. So I think what we'll have to do is teach it as a fine opportunity to teach the using declaration. So one approach would be to invite the student to think about how they might decide their usage policy. For example, if you're making a game, they might decide to put these using declarations in their general maths header file. You can see we're saying our matrix implementation. It uses our regular matrix operations and a regular fixed size matrix of float over n by n. You might be using 2 by 2, 3 by 3, and 4 by 4 matrices in your games. And so those are the three things that you would those are the points where you would specialize just on the dimensions of the matrix. And that's how we'd use it. auto M equals stud matrix, matrix impl, 3, 3. Or you might decide on something like this. That's my preferred approach. So float 3, 3. So this is a matrix 3 by 3 of floating point numbers. It's a stud matrix over the regular stud matrix ops, over the regular stud fixed size matrix over float 3, 3. And that's how you'd use it. And the point is they should concentrate the pain. Okay? There's one place you view these as early policy decisions. So teaching customization is actually very much an advanced topic. You would want to customize if your problem domain warrants something exotic. If you were to create an implementation of Strasson's algorithm, then you can create a new operations class and you can import the functions that you don't want to replace. So there we are. Okay. We looked at linear algebra, and then we looked at how the problem has been solved to date. And then we looked at how matrices can be stored. And then we considered the impact of promotion and conversion on our scalar types, and also the impact of wanting to choose algorithms for different conditions that we might know about. And then we looked at how the API might all fit together. If you're interested in keeping track of how this proposal evolves, that link at the bottom is the committee study group where we're looking at things. SG14, I've been on there for a while. I'm sure some of you know about it. So let's rewind the goals. Provide linear algebra vocabulary types. Parameterize orthogonal aspects of implementation. With defaults for the 90%, customizable for power users. With element access, matrix arithmetic, and fundamental operations. Solving common least squares and eigenvalue problems with mixed precision and mixed representation expressions. I think we've met all those goals. So there we have it. We're still iterating on the API. Indeed, we've made progress since I completed this presentation. So this proposal will offer a standardized API for C++ for linear algebra, separating storage and operations and offering customization over those parts. So Bob and I hope to present the first version of the paper in Kona in a couple of months. Stay tuned. Ask me 2 questions. We have 4 minutes. Go. Yep.
So a short one first. When you were the slide that was explaining the promotions of storage, it said that when you're multiplying 2 views, you get a fixed size.
Yes.
If you have views of dynamic size matrices, then you have to get a dynamic size matrix.
If you have views of
just to check that slide if it indeed is an error, because we have only 4 minutes. I don't have to wait for an answer.
Okay, all right, I'll check that. I think if you're multiplying 2 views, you're going to have to create. And yeah, I suppose it depends on the nature of the view.
Yeah, that's my point.
Okay. Yeah.
The two other questions. One is the underlying implementation of external expression templates.
Yes.
For example, the Eigen implementation. It's full of special cases.
Yep.
So, for example, you have A times B plus C, and that's optimized. But if you write it as C plus A times B, then you get crappy code.
Yes.
I don't know if anybody has thought of a more generic way of approaching this. And the third question is about customization points in really high performance code. For example, in neural networks. Where you have lots of matrix multiplications, but also other memory-like transformations on the same data. So you have a waste of cycles when you perform one transformation on that data, and then the caching block algorithms again transform it to perform efficient matrix implementation, and then to transform it back again into the linear way that you expect a matrix to look like. Consider maybe a customization point that you can interrupt the matrix multiplication algorithm so that it returns data in its cache-friendly blocked representation, so that it doesn't transform it back into the linear, if you understand what I'm saying. Because in such domains, as for example in neural networks, that will enable much more efficient code, because these transformations back and to from like cache-friendly representations could be avoided in chained operations.
Okay, I understand what you're saying, but do you actually have a question?
Yeah, that was a question. Whether you would consider. Sorry, I'm sorry for not.
That's fine.
Whether you would consider for a standardized library to actually be useful in all high-performance computing cases. One of them is the one I tried to explain in neural networks, where you have where you have matrix operations intermingled with other operations.
I understood that part. I just didn't understand the interrogative part of your question. Yes, we've considered all sorts of things. There comes a point where you have to decide how it's for the 90%. We can't imagine that we're suddenly going to see every matrix library is going to be swept aside before us. It'd be great if we could manage that, but it seems really quite unlikely. But that's no excuse to deny simple matrix, simple linear algebra usage to everybody else. It may be that we can do that. As I say, this is first iteration. We're spitballing here. We're trying to work out what the shape is. We're taking input from all sorts of people. Go back to that. Go back to that group and just follow the chain of discussion that's going on there. There's an awful lot of very interested people. If we can manage that, we'd be delighted. But we're not going to abandon the whole thing if we can't manage such complexity. I'm afraid we're out of time. Thanks very much.